It's now time to start talking about the second law of thermodynamics. And this is one of the most important laws in all of physics. And you hear a lot about it, especially today with our energy usage, global warming, and things of that nature. So we're going to talk about what is the second law of thermodynamics. There are several different statements of it, so we're going to discuss those, as well as how to actually apply it to certain systems. Before we get started, let me talk again about the idea of irreversibility. So irreversibility is simply, in the context that we're going to use it in this chapter, the idea that a system cannot return to its original state after it has gone through some sort of process. Okay, so if I have done something to a system, if the process is irreversible, it will not be able to go back to its original state. You can think of cracking an egg and then beating it until it is a smooth mixture, right? So if I crack an egg on the side of a bowl, and then inside the bowl I have the yolk, and then I have the egg whites surrounding that, and then if I take a fork or whatever, and I whip the egg into a smooth yellow mixture, that is an idea of, or that's an example of an irreversible process, okay? So I cannot, through natural means, okay, and when I say natural means, I mean the molecules in the now beaten egg themselves will never separate back out into the yolk and in the surrounding egg white. There's no law that says the molecules themselves can't rearrange themselves that way. They're moving around and they have some motion due to their thermal energy, and their thermal energy is a measure of their average kinetic energy. Those molecules are moving. They're free to collide with each other and rearrange themselves. So there's nothing that says they cannot rearrange themselves into the pre-beaten state, but you will never observe it. Why not? That is part of what the second law addresses. Why don't we ever see these irreversible processes reverse themselves? And we will find that out, not in this video, but in this chapter we will discuss that. So this chapter, the beginning chapter in this video, we're going to focus on heat engines, okay? And that's the statement of the second law that we have here. This is known as the Kelvin-Planck statement of the second law of thermodynamics. And what this statement says is that it's impossible to construct a heat engine operating in a cycle that extracts heat from a reservoir and delivers an equal amount of work. Okay, so in other words, if I have some mechanical device and I bring heat into that device, I cannot use all of that heat to do work. I have to reject some of that heat. Okay, that is what this is saying. So in other words, there's no such thing as a perfectly efficient engine. All right, now the diagram that we're going to use for engines looks like this. Okay, this is a simple model of a heat engine, right? So here I have a hot reservoir, some heat that I can bring in. Here's my engine right here. I'm bringing that heat into my engine, and my engine is going to do some work. And in your heat, or in your engine in your car, the internal combustion engine, the hot reservoir is from the combustion of the gas from the spark plugs. You're bringing in heat, and that heat can do work by pushing on a piston, which turns the crankshaft, and then you expel some heat to your cold reservoir, in this case the atmosphere, right? As the expelled gasoline is rejected through your exhaust system, right? So the QH is your hot reservoir that you're drawing energy from. QC is the cold reservoir that you're rejecting the heat to, and the work done is the difference between the two, right? So what this statement is saying is that the work that I can get out of my system is equal to the difference between the temperature of the amount of heat that I can draw from my hot reservoir to the amount of heat that I have to reject my cold reservoir per cycle. Okay, so that is the diagram of the heat engine. Now, for just a quick second, what this statement again is saying is I cannot have a system where I only draw from my hot reservoir and I do work. This leads to an idea called efficiency. How efficient is my engine? If I could do that, if I could draw all the hot energy that I wanted from my hot reservoir and do work with that total amount of energy, then my engine would be called 100% efficient, okay? But this statement says that that can't happen. So how do we define efficiency? We define efficiency by the amount of work that I can get done to the amount of heat that I have to draw from my hot reservoir. And from this statement, we can see that my efficiency is just QH minus QC over QH. I can rewrite this again as that. So this is a standard expression for the efficiency of my engine. 1 minus the ratio of the amount of heat that I reject to my cold reservoir to the amount that I'm drawing in from my hot reservoir. Okay? Now we want to talk about the Carnot cycle, and the Carnot cycle is a very specific type of engine. It's the engine that has the maximum theoretical efficiency for drawing heat from a hot reservoir and rejecting it to a cold reservoir. And Carnot's theorem says that any physical engine that's built that also uses those hot and cold reservoir numbers, any physical engine cannot have a greater efficiency than the Carnot engine. So the Carnot engine is very important theoretically because it sets the maximum limit for efficiency between hot and cold reservoirs.